Hello everyone, welcome back to my next video. This is going to be problem 31 out of 35 as well as video 31 out of 35 in my set of videos, one for each problem in this AP Physics C Mechanics multiple choice test. So if you've come this far, thank you for watching. Let's finish out strong. So there's a scenario associated with this and the next problem. So let's dive right in. A particle of mass m moves counterclockwise around a horizontal circle of radius r. The angular speed of the particle is given as a function of time t by the equation angular speed as a function of t equals bt, where b is a positive constant and t is greater than or equal to 0. So here we have the diagram for this. There's the radius of the orbit, and then here is our particle moving in a horizontal circle around the center. And this is the top view. Here, let's get a little bit closer so that's clear. There we go. Alright. So question 31 reads, which of the following best describes the acceleration vector for the particle in the diagram? The answers are A, it is directed towards the left, B, it is directed towards the bottom of the page, C, it is directed towards the top of the page, D, it has components directed towards the right and towards the bottom of the page, and E, it has components directed towards the left and towards the bottom of the page. So let's go back to thinking about what concepts are at play here. So this is asking about the acceleration vector. First, what types of acceleration are in this problem? Remember, we have centripetal acceleration, there's tangential acceleration. Let's think about which are present here. So obviously, since this is rotating in a circle, there's going to be some centripetal acceleration at play, as there does seem to be a centripetal force, possibly gravity, pulling the particle in. There's also going to be a tangential acceleration, as it is like moving around instead of just coming in. So I have no space left on this paper, but I'm going to draw a little zone and write the equations for these. So centripetal acceleration, A centripetal, is equal to v squared over r. Hope you can see that. V squared over r. And as such, centripetal force, remember, force is equal to mass times acceleration, Newton's second law. So if we know what centripetal acceleration is, to find centripetal force, we're just going to multiply by the mass. So force centripetal is equal to m v squared over r. So these are some equations we have for centripetal acceleration. We're not actually going to need them in this problem, but these are some of the concepts, the greater concepts that are at play here. So in this case, we have centripetal acceleration, pulling it in, keeping that rotation, and we have a tangential acceleration going this way. So let's think about which direction the centripetal acceleration is pointing. The vector for the acceleration is pointing inwards, because that's what a centripetal force is by definition. It's attempting to pull this inwards, which is what keeps it in this circular orbit. So now let's start looking at our answers. Directed towards the left, well, our tangential acceleration is going this way, but we have another acceleration too. We have another acceleration vector. So it's not solely going to be A. This is partly right. Directed towards the bottom of the page, that is true as well, partially true. There is a centripetal acceleration vector pointing in, but it's more than just that. Directed towards the top of the page, no, not at all. D has components directed right and towards the bottom. Well, in this case, there definitely isn't is not any vector, acceleration vector pointing that way. Nope. And E has components directed left and towards the bottom of the page. That is our answer, tangential and centripetal acceleration with vectors pointing down in this case and to the left. Alright, thank you for watching. Let me know if you have any questions about centripetal acceleration, tangential acceleration, when to use which apply to which situation. Alright, thank you for watching. Make sure to check back in for 32. We're almost there.